we have another keynote speaker, Hector Zenil. He's joining us online. And Hector, he is Associate Professor at King's College London, and he's also Founder and Chief Visionary Officer at Oxford Immune Algorithmics. He has a very interesting CV. He actually has 2 PhDs and have a scientific impact in several disciplines, including computer science, medicine, and aging research. I met him in 2013 at the Wolfram Science Summer School. He was one of the lecturers and mentors there. And then he had already worked with Wolfram Alpha. And I think since then also worked a little bit with the teams behind Siri, Alexa, and ChatGPT. And today he will talk to us about not all patterns are equal, how complexity theory can evaluate and improve AI. So thank you very much, Hector.
And I want to thank first of all the organizers and Andreas and Christian for their kind invitation. And I'm really sorry that I'm not there in person, but I'm traveling to Japan today to give a series of talks, and it was difficult to go into Norway first. But I'm here very happy to talk to you about how not all patterns are equal and how complexity theory can evaluate and even improve AI. So one of the first things I wanted to share with you is kind of my vision about science, complexity science, and to some extent AI, which I think most of us would agree is basically to make sense of the world, or to understand the patterns in the world. And here on the screen, we have 2 pictures that I took a few years ago from the north of Ireland and the north of Scotland. One is called a fairy ring. I don't know if you have had the opportunity to see one of these. It was striking for me because I had no idea what was it, and I took a picture, and later on I Googled what could it be, because this was mushrooms that basically were arranged in a circular fashion. And actually what I learned was called a fairy ring is not as round as many of you can find online. So it is kind of very interesting. And then we have also the basal columns that are perhaps more popular. This is the Gaian Causeway in the north of Ireland. These are hexagonal columns, and even when you see only like 10 or 20 on the screen, there are thousands of these, or hundreds of thousands in each place. And both of them come from very different causal mechanisms. And I think science is pretty much about finding these patterns and trying to understand and explain them. In the case of the fairy ring, for example, these are mushrooms that start growing at the center. They exhaust the resources and they start growing to the periphery and basically arrange themselves in this shape. In the other case, it is lava that gets into contact with a source of cold water, and is very similar to the process of soap, for example, that you see these kind of hexagonal patterns forming. So in one case, there's living systems involved and a kind of symbolic pattern, which is a circle. And in the other one is completely a physical process with no living systems involved, and builds this kind of almost human-like patterns. So one question is obviously where this kind of complexity comes from. And you know the traditional story is that complexity is an emergent property of many particles interacting with each other. And I've been trying to find some other explanation because I'm not quite convinced by that one. And I think actually complexity is an emergent property of universal computation. Because even when you have very few elements, and you can see on your screen what is called an elementary cellular automaton. If you're not familiar with this, it's basically just a computer program that is very visual in its evolution. It runs from top to bottom. At the top, you have some initial condition, and basically you apply some rules. In this case, these rules. And these computer programs are very easy to describe. As you can see on the screen, basically the rule requires just 8 bits to be described, because the first part is basically a fixed part that, in which you can describe all the computer programs in that space. And even when the computer program is very simple, it has been proven to be Turing universal, which means that basically it can compute any Turing computable function including things like running computer programs like Windows or you name it, Word or Excel or whatever it is. Obviously, it would be incredibly complicated, very slow, and impossible to interpret. But in principle, you can run anything on this very small computer. And yet, we have so few elements to begin with. It is true that it leads to many particles and elements that interact with each other. But I think the cause is basically the rule itself. And something we found and published in this very nice paper is that pretty much every computer program, no matter how simple it is capable of universal computation. So what we did is Stephen Wolfram categorized the behavior of these computer programs in 4 classes. So class 1, for example, is a very simple type of computer program that in no way could have been believed to be able to emulate a complex one. And by complex, I mean something that produces random looking patterns, for example, or is even capable of universal computation. What we found is actually that they seem they can. If you find a compiler, and you can see the small compiler on your right, a compiler is basically another small computer program that you put at the input of the original computer program. It's of fixed size, and it doesn't really do any computation. It's just like a translator. And what we found is that you can pretty much always find like a compiler to make all these computer programs, no matter how simple, to compute more complicated classes, including class 4. So we have even here class 2 that are supposed to be very simple, emulating class 3 that is supposed to be random looking, or class 3 also emulating class 1 and 2. So basically we're breaking the classes. It is true that we didn't find some cases, but that doesn't mean that they don't exist. The evidence actually shows that if we keep exploring the space of possible compilers, we will find it. And that's because if we go to a slightly larger computer program space, because basically these are only 256 small computer programs, many of them repeated because they are complementary or the reversion of each other. But as soon as you go a slightly larger space of computer programs, you start breaking those classes again. So you can see here, for example, class 2 computer programs emulating class 4 computer programs that are believed to be Turing universal. There's some trade-off. So computer programs that are too simple or too complicated have some difficulties in, for example, emulating class 4 automata. So we are not saying that we have flattened everything, but we have broken kind of the fundamental classes that were believed to exist in this space. And basically this means that in some very strong way, we have empirical evidence of pervasive Turing universality. And this plot basically shows that by increasing the size of the computer program space, you keep finding more and more small compilers that make any simple or complicated computer program to compute anything else. So this is the percentage of how much they can emulate in their own space. And when you have these rules that are able to emulate other rules in the same space, that is called intrinsic universality. And actually that kind of universality is even stronger than Turing universality, which means that intrinsic universality implies Turing universality. So this is a very strong and interesting finding. So one question is, how can we characterize all this complexity? Do we need more metrics of complexity? We have so many, almost every group or even person comes up from now or then with a new complexity measure. And what we are suggesting and proposing is actually that we may not need new ones, but actually a better understanding of how they relate to each other, especially their interplay or their hierarchy. And we have some work related to this. We have found that pretty much all of them are connected in one way or another, sometimes more complicated than others. And I'm not going to go into the details. But for example, we have done a lot of work on relating Shannon entropy to algorithmic Kolmogorov complexity or fractal complexity, time complexity, They are all very interesting connections, and I think has been an area that has been neglected, and it is something that we should do more as a community. And that is because each method basically tries to characterize a different thing. So here's an example of a few of them. So with classical probability, we can say, oversimplifying, that we are basically trying to measure how likely an event or an object is. With Shannon entropy, one way to see it is how diverse an object or event is, and so on. So basically, each complexity measure is trying to capture some aspect of the observation that we are making. And one question is whether there's complexity metrics that are more powerful than others, or even include or can characterize all the patterns at the same time. And we will see that actually there's one. So to show you that not all patterns are equal, let me give you some examples. Here on your left, we have a set of sequences. One of them is, for example, the alternating sequences of a sequence of zeros and ones, which has a very simple generative mechanism. Basically, it's print 0, 1, and a number of times. So this pattern actually gives away its generating mechanism because it is visually very simple. And in that way, it is statistical because the sequences itself has patterns that give away the simplicity. But there are some other patterns, almost as equally simple and also generative, that are kind of hidden from the patterns of the sequence. So for example, this one is called the 2-more sequence. And the way you build it is by starting with a 0, and you binary negate the first segment of the sequence. So in this case, we started with 0, so the next bit is a 1. So now the new sequence is 0, 1. So the binary negation of 0, 1 is 1, 0. So we concatenate it again, and we keep going. And basically, this builds an infinite sequence. Well, it turns out that this very simple sequence is what is called Borel normal, which means that there's no overrepresentation of any subsequence of digits in this sequence. In other words, this is also a sequence that has maximal Shannon entropy rate, which means that no matter which statistical metric you use, you are not going to find anything interesting to say about this sequence. Yet it is causally generated. And I'm calling this non-statistical because basically the sequence is not giving away its origin if you didn't know it in the first place. And by that, I mean you are an observer, basically looking one by one the digits coming to you and trying to make sense of what you are seeing. In this case, you would be able to almost immediately find out that there's a regularity, and that may come from a generative mechanism. But in the general case, this is actually very difficult, and it's basically what we do in science, to make an observation and try to make sense of it and find the cause for that observation. And I can come up with many other examples. This is another sequence that is called Champer-Ohm constant, which is the concatenation of the natural numbers. And again, this is proven to be Borel normal. Again, maximal Shannon entropy, what comes with from a very simple function, which is a successor function. This is another example. So this is a segment of pi in decimal from a BBP formula that basically shows that you can calculate any segment of pi without having to calculate the first digits. So a very interesting formula. And again, this for all purposes looks random, but comes from a short formula in the sense that if you require more digits in any of these cases, you don't increase the number of description of the formula. And then there are some cases in which you can, some sequences may have been generated at random, and you cannot really compress them. So the shortest description is itself. And what all these top sequences have in common is that they are all generated from causal origins, but some of them give away very easily their origin, and some others they don't. And actually, human minds, and we have a very nice paper about it, exploit non-statistical patterns. One way to see this is basically, for example, the way in which you memorize telephone numbers. If a telephone number, for example, has only even numbers, it is very easy for the mind to remember, even if it may not have a statistical pattern or regularity. And this has all to do with science. And different descriptions that we do in the practice of science. There are some descriptions that are completely statistical, like this famous example of how car times between each other distribute, and it turns out that they distribute as a Poisson distribution. But usually in textbooks, they don't give you the reason, and the reason is actually quite trivial. But if you don't know it, you may think, well, this almost looks magical, like people actually go out at the same time, because this basically means that the space between cars is very short, and basically they come in batches. This is as opposed to a mechanistic model, which basically is telling you the how and why, even if it could be completely wrong, like in the geocentric model, for example, explaining the solar system. In the case of how cars distribute the space between them, the explanation is very simple. There are always slow drivers, and basically people accumulate behind them. And the way to prove it is with interventions. So if you add more lanes, basically you destroy the distribution. And actually you can recover the distribution if you crowd the street again with many more cars, because then you have again this phenomenon in which you have cars that are slower and keep holding back the ones behind. But in the case of the statistical description, you always need like the interpretation from the human being. Because the interpretation of the human being is basically, in the case of the statistical distribution about car length, basically the one that is giving the explanation and not the metric itself. The metric is just descriptive. So in an ideal scenario, you would have a metric that actually tells you something about the cause and not only describing the phenomenon. And ideally, you should have also some method in which you can derive some sort of model like you have on the right, which is a set of differential equations. And to this process is basically called symbolic regression, because what you want to have is an observer equipped with some sort of metric or method that when making an observation, the two together can come up with some model. Again, I'm basically describing what we do in science and what science is about. It is about inverse problems, making an observation and coming up with an explanation. And so far, we have been using a lot of methods based on Shannon entropy, including in AI. So most of the, if not all of the approaches with deep neural networks, for example, use as a loss function a Shannon entropy function at their core. And in this other paper, what we showed is that Shannon entropy is completely object dependent. And to do so, what we came up with was this graph. This graph was built by starting with a node. Each node has a label. And every time that you add nodes, what you try to do is basically to complete the previous nodes so that the number of edges corresponds to the label of that node. So for example, in step 2, we have node 1 that has 1 edge, node 2 has 2 edges, and node 3 that is in blue because it is still incomplete, only has 1 edge, but in the next step, basically we complete it and we add 2 more edges so that the third node has 3 edges. So this is a completely deterministic process. And we built this graph on purpose this way because basically the degree sequence has maximal entropy because it's the Champeron constant. So 1, 2, 3, 4, 5, and so on. So if you plot the degree sequence from which you can reconstruct the original object, it has maximal entropy if you don't know the generative mechanism and you don't have access to the probability distribution. But if you plot this graph as an adjacency matrix, all the nodes basically accumulate in a diagonal, which means it is low Shannon entropy. So we have 2 ways to describe the same object that have divergent Shannon entropy values, and even when this is a deterministic graph. So 2 ways to describe the same object with 2 divergent Shannon entropy values. Again, you could say, well, this is deterministic, so we already know it is low Shannon entropy, but the case is when you are an observer, you don't have access to the probability distribution. You are looking at this object being built on the fly, and you don't really have access to the cause for this graph. So this is what happens in the most common scenario. You have an observer that usually doesn't have access to the cause, but that would be the ideal case scenario, that you actually know how this, in this case, this computer program, another elementary cellular automaton, was built. And what happens most of the time is that we are only looking at partial evolution of that system, and we don't have access to the generative mechanism. But one thing that I have proposed is actually algorithmic probability is a theory of causality. And the definition of algorithmic complexity is this formula that I'm going to describe in the next slide. But this metric is related to mathematical randomness. So it is a mathematical accepted definition of randomness, because it's basically telling you that if you cannot compress something, then it is random. So most people associate this metric with randomness, and that is right. But actually, the way I see it is that it's telling you what to discard, because you want to discard everything that is random, that is not interesting. And then you also can characterize what is trivial with this metric and other metrics. So all the statistical regularities that we can characterize with Shannon entropy fall into the trivial case for our purposes and basically can be discarded. It is still causal, but it is not the kind of more complicated causal content that those metrics fail to capture. So at the end, you are left with this middle set of interesting cases, and I'm going to explain a little bit more about it. So this is the definition of algorithmic complexity, and basically it tells you that if you have an observation S, the Kolmogorov complexity is the length of the shortest computer program, computable explanation, that running on a universal constructor basically reproduces that observation. And the constructor, by the way, doesn't have to be a Turing machine with a head or a tape. That is a common misconception, because people think that this formula is very niche because it requires like a Turing machine and only applies to binary objects and sequences. That is not true. Actually, all the theory about Turing machines, both the universality results and the theory of algorithmic complexity, is all about discarding those elements because they are not very important. So you can have, for example, an elementary cellular automaton instead of a Turing machine that doesn't have a tape or a head, and it is actually parallel. So as long as you have a universal constructor, you can apply algorithmic complexity, and you can always discard the length of the universal constructor. And then something very interesting is that this formula is always described with trying to find the shortest computable explanation. And that basically introduces uncomputability, because if you want to prove that something is the shortest, it's basically impossible in the general case. And that's why this process is considered to be uncomputable in general, which means that you cannot create an algorithm that always gives you the Kolmogorov complexity of an observation. But in my point of view, if you, and this is mathematically provable very easily, if you relax condition of finding the shortest computer program, then immediately this process becomes computable, because you can always put more resources into actually finding a shorter computer program, or any computer program for that matter. And that is actually the most interesting case for me. It is not really about finding the shortest computable explanation for the observation. That was very useful for proving mathematical theories about the theory of algorithmic complexity, but in practice, what we do in science, we are not looking, I mean, eventually we are looking for the shortest theory. For example, this theory of everything that we think that it may exist and may be very short and able to explain everything. It is basically an analogy of exactly this kind of formula. And in the ultimate goal may be that smallest explanation, but it doesn't have to be the smallest to be useful. And the plot on the right is basically just to explain that this is not niche, it's not only about computer programs, because actually everything that we know in mathematics can be written as a computer program. It doesn't mean that the computer program has to halt, but you still have a procedure that you can follow step by step, so it is mechanistic. So when we are talking about computer programs, basically this is regulating and governing everything else that we know in computing science and mathematics. And Kolmogorov complexity, or the other side of the coin that is called algorithmic probability, as we will see in the next slides, is basically describing this practice of science of moving things that we thought that were or looked random, in the first place, like, for example, the Greeks, how they wondered how planets moved on the sky, and actually the name planet means errand in Greek. And then with science, basically, we moved many of these things that looked almost like magical to the world of having an explanation or a model for it. That has basically been the history of science in my perspective. And then there has been these unifying principles where we thought that perhaps something that looked completely random, like the way in which planets move, related to something as random as why objects on Earth fall down, turned to be completely related and be part of the same phenomenon. And that's the power of science and basically explaining more with less. And that's exactly what algorithmic complexity and algorithmic probability is capturing. So that's why I think it is a fundamental concept in causality. You may also think that what happens if I change the universal constructor? Maybe I get completely different results. The computer program will look completely different. The length will look completely different. Well, we have a very nice and important theorem called the invariance theorem in Kolmogorov complexity that basically tells you that that is not the case, that at the end they are going to converge and that they are bounded by a constant. Obviously, we don't know how large or small that constant is, but we have done a lot of experiments and we know that in general, it is very small. So we have run these processes with different models of computation, for example, Turing machines, cellular automata that we already saw, post-tax systems, which is another model of computation, completely different between each other. And basically they produce about the same distributions. And when you look at the values of the complexity and the computer programs that they produce, basically the top half, which is the most frequent, coincides between each other. And the second half starts converging as well, as long as you keep computing more and more. So it is very well behaved, even if theoretically we can never guarantee that the constant is very small. And all this theory has already produced some very interesting results. So for example, there's this Lee and Vitani interesting paper on reconstructing phylogenetic trees. This is a landmark paper in 2005, where they show that they could use compression to reconstruct these trees that were found to correspond perfectly with the knowledge we have in molecular evolutionary theory. And has been used to many things like plagiarism detection, fraud detection, map feature detection, and so on. We ourselves have also some work on this regard. For example, for the problem of nucleosome occupancy, which is the second most important problem in molecular biology, only after protein folding. But another misconception is that actually Shannon entropy or entropy rate and statistical compression can approximate algorithmic complexity in any meaningful way. And that is basically because statistical compression, in particular things like LZW, which is behind things like your zip files and just zip and all those computer programs that are able to compress data, they are completely related to Shannon entropy. So they are not more related to algorithmic complexity than how Shannon entropy is related to Shannon entropy in the first place. So they are not adding much to the table. And actually, in many cases, there are very bad approximations of algorithmic complexity. So the question is, of course, if we can do any better. And actually, we can, and this is what we have been working on for the last 10 or 15 years. The idea is based on this concept of algorithmic probability, which, by the way, turns out to be completely equivalent to algorithmic complexity or Kolmogorov complexity, which is what we have seen in the previous slides. This concept was introduced by Ray Solomonoff in the very famous workshop in Dartmouth College in the 56, where the term AI was coined and where people consider artificial intelligence basically was started. And this theory for me and the people doing computer science is basically the theoretical solution to artificial intelligence, because it's the optimal theory of inference, in particular abduction. Abduction basically means that you can make the most optimal inference based with the data that you have at hand at that moment. But let me explain algorithmic probability. You may remember this whimsical infinite monkey theorem, right? This idea that if you have a source of randomness, in this case a monkey, you can try to estimate how long a monkey would take, for example, in producing the works of Shakespeare. And even a single paragraph of Hamlet would take, usually, if you do the math, longer than the age of the universe. But things actually change dramatically when, instead of thinking that the monkey has to type letter by letter on a typewriter, things change very much if you replace the typewriter with a computer. And instead of every keystroke being a letter, it is actually a letter for a computer program. So basically, we have a compiler on the computer and the monkey typing on the computer. Then, if you ask, for example, what is the probability of producing the digits of pi, the mathematical constant pi, if you wanted to produce one by one, the probability would dramatically go down as a function of the number of digits that you want to get right. So it will be 1/10, because it's the base in 10, to the number of digits that you want to get right. And so the first 100 digits will be 1/10 to the 100th. So very small, the longer the digits you want to get right. But if you place the monkey on a computer, then the monkey has to type and get right, not the digits one by one, but the computer program or the mathematical formula that produces pi. And because pi is low Kolmogorov complexity, because it has many short descriptions, there are short formulas and computer programs that can produce pi. Then things reverse dramatically, because now the probability that now is called algorithmic probability of a monkey typing a formula that produces pi by chance is very high, because it has a very short description. And now actually the probability is 1/2, because usually you measure computer programs in binary, to the length of the computer program. And that concept is very powerful, because I just connected complexity with probability. And actually, the relationship with algorithmic complexity is the inverse, the inverse logarithm of the algorithmic probability. Here, m is the algorithmic probability. And this is related to many things, including Chaitin's omega number, which is called the infinite wisdom number, because basically you can capture all knowledge in this very powerful concept. And this is just not a random metric. Even Marvin Minsky, a few years before passing away, said this: "It seems to me that the most important discovery since Gödel was the discovery by Chaitin, Solomonov, and Kolmogorov of the concept called algorithmic probability, which is a fundamental new theory of how to make predictions given a collection of experiences. Everybody should learn all about that and spend the rest of their lives working on it." So basically, he was kind of almost regretting not to have spent his life, and Marvin Minsky is basically considered perhaps the most important founder of artificial intelligence. He was regretting not to have spent more time on this fundamental theory. So it's really very important, and Minsky was basically telling what I've been doing for the last 15 years. So that my own career has been about studying algorithmic probability. So obviously there are many ways, difficult ways in which one can try to estimate Kolmogorov complexity, and by means of algorithmic probability, and the other way around. And we can come up with a very interesting way to approximate it. And the idea is to basically chunk something into smaller pieces. I'm not going to go into the details because it can get too technical. But if you have an object, basically what we do is to divide and conquer and try to find small computer programs for different small pieces of the original observation. So here's an example. You have a causal system, and basically you sample that system to try to find out small computable hypotheses for how that system may be working. And if you find them, basically you have sufficient proof of causality, as opposed to something happening actually at random. And the algorithm actually traverses the whole thing in this way, and there's a lot of technicalities behind how to deal with the boundaries and so on. But this is just an idea of how we actually do this in practice. how we traverse an observation or an object to try to find out what we call causal patches. And we can do it not only on sequences, but on anything else, including matrices. And matrices, as you know, can represent networks or images. We can do it on vectors and tensors and pretty much anything that can have a description. These methods basically work because if you have an object that is causally built or generated, it has a simple description. And if the whole has a simple description, the part also should have a simple description. And we have a nice theorem about it. And the opposite is also true. If you have something random, there is no way in which you can cut something random in which all the parts don't look random and suddenly are causal. So that's the justification of how we divide and conquer these problems. And this is common in computer science and the theory of algorithms. Is basically what is called a greedy algorithm, that you divide your larger problem into smaller ones. And the way we do is that we explore the space of computer programs. Well, we do it with some guidance. And we have combined all this with perturbation theory. So kind of the ideas of Judea Pearl to basically try to guide the search of computable models explaining an observation. And we have many examples in which we can show that we have found mechanistic explanation for something that looked random and couldn't be characterized with things like Shannon entropy. This one is an example, which is again the concatenation of natural numbers. And then in this case, because we are using an example with binary sequences, we can convert it to binary, that sequence, and we find actually the computer program, which is a binary counter with a state diagram, state space description, that basically tells you how this sequence may have generated. And actually, we don't only find one description, but sometimes thousands behind an observation. We can sort them by complexity. And by Occam's razor, which is also justified by Kolmogorov complexity, we can keep the simplest ones and test it against the observation, the new data. And this is the way in which we update the universal Turing machine to basically implement Bayesian inference. So we have here on the screen some of the cases that I'll show you at the beginning with the original sequences, and how with a universal Turing machine, basically we can describe each of them and find the generative mechanism. We have done it even for the digits of pi, for example, and we have shown that actually we find some signals in pi that tell us, give away its causal nature. So how do we do in AI, for example, for prediction, in sequence prediction? We tested ourselves with the best time series transformers around, like TimeGPT and Kronos and so on, in a very small case for binary sequences, because this is computationally very expensive, and we definitely don't have the money that these people have for LLMs, which, as you know, it is in the order of billions. So we only had to focus on a small toy example with random binary sequences that we knew some of them had causal explanations, and whether we could find that causal explanation and actually make predictions. Because once you have the generative mechanism, you can run it in reverse to try to find the next element. So once we have the model, we can also make predictions. And actually, the theory of algorithmic complexity also tells you that compression is equivalent to prediction. If you are able to compress, you are able to better predict. And if you are able to better predict, is because you have understood something about the model that allows you to also compress it. So we are outperformed and did very well on this small binary data set against not general purpose LLMs, but LLMs that are specialized in time series prediction. And then we assumed that we could do the same for generalistic LLMs and specialized, and basically get all the cases right in the limit in order to evaluate whether other frontier models actually are justified at telling us that they are about to reach artificial superintelligence. We chose artificial superintelligence because AGI is more difficult to characterize. But ASI for us would be like optimal prediction. So in our definition, this is how far these guys would be. And then we also found something very interesting, that new models, and this is not the updated plot, but for example, ChatGPT 5 did less well than ChatGPT 4.5. So there's some sort of regression in new versions. And that was not only with OpenAI, but also with Claude and a few others. So that may suggest that actually they have found this hard wall that some authors believe they have reached. But we think that our models basically can improve based on this evidence and all this theory and complement neural computation to come up with neurosymbolic computation. And we are applying all this to predictive medicine and early detection. So we have built, for example, our own blood testing machines that are working in hospitals in the NHS, believe it or not, coming all the way from completely abstract and theoretical stuff, all the way to having a device in hospitals today that are exploiting this theory to basically come up with potential explanations of how we transition between health and disease. And this was basically a spin-out that we founded at the University of Oxford and has been around for a number of years. But I'm going to stop there for in case there are any questions, and not before recommended you, if you are interested in these topics. We published a couple of years ago 2 books on exactly this topic. So thank you very much.